So today we are looking at the basics of molecular orbital theory. All molecular orbital theory is a different way to describe bonding between atoms in covalent compounds. Yesterday we looked at hybridization, and hybridization, the individual atoms basically contributed their valence orbitals to the hybrid, creating brand new orbitals used in bonding. Molecular orbital theory is a little bit different in that here the contributing atoms merely overlap their current orbitals with the current orbitals of other atoms, and they don't create new hybrid orbitals. So this theory is not very useful in helping us understand shapes and bond angles and things like that. It's actually more useful in some advanced topics, which we're not really going to concern ourselves with. We are scratching the bare minimum in regards to molecular orbital theory, so just know there will be a lot of holes, but there's very little you need to know to be successful on the AP with this knowledge. So starting out, here's an example of two atoms about to bond, both of them being 1s orbitals. Well, their electron being in a 1s orbital. For instance, this is probably hydrogen making H2, H and H coming together to make H2. So we've already learned to define this orbital as an area of high probability that an electron can be found. Well, this area of high probability is actually defined by something called the wave function. And so we define that shape based on the wave function. Well, if we're going to combine two orbitals, one of two things can happen. We can add the two wave functions, or we could subtract the two wave functions. If we add the two wave functions, we create what we call a bonding orbital. It's of lower energy, and we consider it bonding because, and I'm actually going to kind of draw a picture a little more indicative of it. If you look, the highest probability of finding an electron is going to be somewhere near the nuclei between the two. So you can see how bonding can occur if this nucleus's electron is over here and this nucleus's electron's over here. You can see how that would create a pretty good bond. So this is a very stable scenario. Since all these bonded electrons are closer to the nuclei, it also gives them lower energy because they are more stable. So a bonding orbital is more stable. We call this a sigma bonding due to the fact that just like yesterday, sigma refer to the sideways, the side-to-side, or head-on, I should say, head-on overlap of two orbitals. And that's what's happening in both these scenarios. The two orbitals are just coming together, bam, head-to-head. Up here, with the subtraction of the two wave functions, we get something called an antibonding orbital. If you look, antibonding orbitals gives the high probability of electrons to be located away from the nucleus of the other atom. So really, truly, no bonding can really occur because there's a very, 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 very low probability of electrons being shared. So this is considered to be an anti-bonding orbital. The anti-bonding orbital is indicated with a star. So this is a sigma 1s. 1s is because this is a 1s electron we're dealing with. And sigma 1s star means it's a sigma bond, first level anti-bonding. That's what the star is. All right, so let's go and look at some p's. Same kind of thing happens as the p's in orbitals that have more electrons other than hydrogen. Those p's can overlap. If you look here, we have two p's both on an x-axis. And for them to overlap, they would overlap in the same head-to-head fashion. So we're making sigma p's in this case, a sigma p and a sigma p star. Again, high probability of bonding electrons. So this is a bonding orbital. Higher probability of electrons not even near the nuclei, so therefore that is an anti-bonding orbital. We can then look at the other two types of p's. Py and pz are actually more vertical, so in order for them to connect, we're going to get that sideways overlap. And if you remember from yesterday, the sideways overlap was an indication of what we call a pi bond. So here we have a pi p and a pi p, a pi star. So this is our bonding down here, and this is our anti-bonding. All right? So what do you need to know from all of this? It's really not hard. You're always going to be provided, at least I am in this class, I'm going to provide you with this diagram. What this diagram is kind of like an electron configuration for molecular orbital theory. These molecular orbitals are all listed in order from low energy to high energy. And you are going to fill them in order from low to high, and Hund's rule applies. That's pretty much all you have to do. And from this filling in process, you're required to do the following. You need to be able to calculate bond order, and I'll show you how to do that when we get there. You need to be able to tell me the relationship between bond order and molecule stability. The higher the bond order, the shorter the bond length, the greater the bond energy is also important. Looking at the molecular orbitals, once the molecules come together, I want you to tell me if the molecule is, once the atoms come together, I want you to tell me if the molecule is paramagnetic or diamagnetic. So let's go ahead and practice. I'm going to go back to this one. Well, no, I'll just go to a fresh one. We're going to practice and we're going to do H. We're going to make H2. So for H2 to come together, we have an H coming together with an H. What you have on these outskirts here, these lines, they're just little tally places for you to insert the electrons that the atoms have before the bonding occurs. It helps you keep things straight. And so it's basically just normal spin diagram filling here. So each hydrogen is going to contribute 1 electron to the bond because there's only 1 electron in a hydrogen. So that hydrogen is going to submit 1, and this hydrogen is going to submit 1. Now, when bonding and when the overlap occurs, we have, remember, the addition or the subtraction of the wave functions to make bonding or antibonding. So if you look, we only have 2 electrons, 1 on each side, to throw into the pot. We're going to throw everything from the side into the pot. So we're going to throw in 2 electrons, and we're going to fill from low to high all the way up the chart. In this case, 1, 2. We only have 2 electrons, so that's all we can throw into the pot. So looking at just our pot, in the middle portion of this is all we're going to focus on when we now figure out bond order and such. So bond order is the number of bonding electrons minus anti-bonding divided by 2. So looking at this, remember our stars are anti-bonding. So this is bonding minus anti-bonding. I don't have any. So it's 2 minus 0 divided by 2 gives me a bond order of 1. Okay, so what does that mean? Well, it's hard to say what bond order means until you have something else in reference to it. I kind of have an idea of what it means, but I don't want to tell you yet. I want you to see some other examples before we go on. So I'm going to do another one. I'm going to make, let's do O2. O2, for example, would be an O combining with an O. Now, I know O only has 6 valence, but we're not looking at valence. Because we're starting at the 1s level, we're looking at the full number of electrons found in O, and that would be 8. So for each O, we're going to fill in 8 electrons into our little tally here. 1, 2, 3, 4, 5, 6, 7, 8. And the same thing here. Okay, so now we're going to throw the electrons into the pot. In this first pot, there's 4 to throw in, so we're going to put them in 1, 2, and then 3, 4. Remember, you fill from low to high. We have 4 to throw into the second pot. 1, 2, 3, 4. 1, 2, 3, 4. And in the last pot, we have 4 plus 4 is 8. So we're going to put 8 into the pot, and you fill them low to high. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now what we're going to do is we're going to calculate bond order. We have bonding electrons. I'm going to circle those in green. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Minus anti-bonding electrons. 1, 2, 3, 4, 5, 6. Divided by 2 is 2. So O2 has a bond order of 2. One thing I forgot to mention on the last slide was the fact of magnetism. This is paramagnetic because in the pot, there are lone electrons. I don't care what's going on outside the pot. Outside the pot is prior to bonding. We care about after the molecule's bonded or created. Next, let's just go back real quick. I want to talk about this one. This, because all the electrons in the pot are paired, is diamagnetic. Okay, we'll do a couple more quick examples. So let's try nitrogen, N and N. So each nitrogen has 7 electrons, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. And we're going to put them in the pot, and we're going to get 1, 2, 3, 4, 1, 2, 3, 4, and this is going to be 6. 1, 2, 3, 4, 5, 6. All right, bond order, bonding, 2, 4, 6, 8, 10, minus antibonding, 2, 4, divided by 2 gives me 3. So I have a bond order of 3 for nitrogen, N2. Para or diamagnetic, this is diamagnetic. Everything is paired in the pot. Okay, so I want to talk about the relationship between bond order and bonds. So if you think about H, its Lewis structure looks like this. O2's Lewis structure looks like that. Nitrogen's Lewis structure looks like that. And if you revisit the bond order, those are the bond orders we calculated. Do you see a connection there? I'm not going to tell you what that is. I'm hoping it jumps out right in your face. If you have questions about it, you can come ask me. But I want you to think about that. And I also want you to realize that as the bond order increases, the bonds get stronger, and the bonds get shorter. You're going to be doing a POGIL activity over the break that will emphasize all of this bond energy, bond length, and bond strength, and it'll be a little more clear to you. And it also will address this little trend I want you to be able to see right there. Okay, one more really fast one. It's going to be a small one. It's going to be Ne2. So we're going to combine neon and neon. If you remember, each neon only has 2 electrons, so I have 2 for those neon. This neon has 2. So then I am going to, why am I doing neon? Sorry, I'm really tired today. We're going to do helium is what I meant to do, He2. He2 has 2 electrons. So each one has 2, so I'm going to do 1, 2, 3, and 4. So helium has 2 each. Let me change this here to get this all straight. All right, so if we were to calculate, this is obviously diamagnetic, everything's paired in the pot, and if we're to calculate bond order, bonding electrons minus antibonding electrons, isn't that 0? Right, it's 0. 0 pretty much means doesn't exist, and that makes sense. Helium cannot bind with anything because it only has an s orbital and it's already filled with 2 electrons, so it can't expand its valence and it can't share any additional electrons. So that's just a little example of how bond order can give you some clues about things. And that's it. That's all you're responsible for. You have some of these on your homework to practice, and then we have a group quiz on Monday.